And this presentation will follow 4 parts. In the beginning, I will describe to you one explanatory technique used in computer vision, on which we will be focusing. And then I will talk about a variation of standard diffusion framework, which I will show is actually effective in explaining predictive models in some specific scenarios. And I would like to finish with some conclusions, which will be like research directions that I encourage you to undertake in the future, because we need to solve XAI, right? This is the main goal. Okay, so a very intuitive explanatory technique in computer vision are visual counterfactual explanations. So it is often thought that we as humans think in this way, that given an image, if you want to explain what your model thinks about this image and how this model takes up its decision, you could semantically modify this original image minimally so that the decision of the model changes, but you observe the semantic features that were modified, right? So here, in the beginning, F represents the classifier, and it simply says that the person on the left is, with high probability, smiling, right? And then you apply some algorithm, the person, let's say, stops smiling, and you actually see that the model changed the decision, so you would say that you trust your model better in this case, right? Now, previous works apply diffusion models. This is not a mystery, right? And it's actually pretty intuitive, because in computer vision you need some prior to move in the image space, right? You can just add noise to an image and accept that it will be semantically meaningful, because it's not. So you need generative priors, and because diffusion models are state-of-the-art, you simply use them and apply them to the problem. So the image on the left you already saw. We will be focusing on this dog, or no, is this a cat? I don't know. In a moment. But another big assumption of previous works is that when talking about the predictive model, they assume white box access. So this was also mentioned in the previous talk. White box access means that you have access to your entire predictive network, right? You can use the weights, you can backpropagate through it, compute gradients, and so on, so on. So this is like a pretty big assumption, because let's be honest, like, I don't know what ChatGPT is actually inside. I can't use the weights. So there are realistic scenarios where this assumption is invalid, where the only thing that we can actually do is query the model with an input and observe the outputs, let's say in the form of logits, right? So this is one issue. The other issue is that for each image, the explanation is generated independently. So just theoretically, let's hypothesize that maybe there is some link between the explanations, because we still explain one single model, and then maybe we should just look for them, because why not, right? So now, central question. Can we actually synthesize those visual counterfactual explanations assuming only black box access, and simultaneously actually find those links? This would be some step forward in improving those explanations. So now I want to talk about the diffusion model that we are actually using for this problem. It's not a very standard diffusion model, because it's called a diffusion autoencoder, and it was published at CVPR 2022. And it's a very interesting concept, because as you could see in the previous talks, diffusion models operate in the same dimension as the images. Optionally, you can map images to the latent space, but still you are always working on the same dimension. And it's actually a pretty bad space for image editing. Like, moving in this space does not allow precise edits, and people in the very beginning were actually blaming diffusion models for not being able to do that. So these guys came up with a very simple idea. Let's train another encoder with the standard denoising network and condition the denoising process on the output of this encoder. So if we structure this encoder to be actually compact, have its outputs compact, then we may expect that this new space will provide us some new features. And this is actually true. So Now, if we attach this another encoder, we separated the representation of a given image into two components. One is the high-dimensional noise, which influences the final result, as you can see on this slide. So varying the stochastic noise actually only influences very small details. And yeah, this is like non-obvious for me. But it turns out that the compact vector that you actually extract from the encoder contains most of the semantics of the image, right? And moreover, there is a very nice property in this semantic latent space that there exist so-called global semantic directions. So you can actually find directions in this semantic latent space that encode concepts globally, like smile or wavy hair. Moving along a single direction always influences the waviness of your hair, for example. Okay, so you may have actually guessed that this is what we will be talking about because the topic of the talk is global counterfactual directions, and it's actually a pretty simple extension of that. But we will be focusing on black box predictive models in this case. Okay, so how can we utilize the existence of this semantic latent space to explain predictive models? So we can actually invert a given image into its two-part representation, right? You can obtain the semantic latent vector, which is the compact part, and the high-dimensional noise, from which you can degenerate the image back again with your diffusion model deterministically. So this is nice. Now let's try actually freezing this part. We know that this part only influences very small semantic details and does not actually give you much control over the semantics. So let's just keep it in place and focus on the semantic vector. So now you can actually observe that if you perturb this representation with some Gaussian noise, you can obtain the variations of the image, right? What's more interesting is that here there's a clear dependency between those perturbed vectors and what you get at the output, right? Because you still keep the high-dimensional noise fixed. So our idea was to actually use this property and say, okay, now I can locally perturb the image, get semantic variations, and like check what is the influence of those semantic variations on my predictive model, which is depicted as this red box, right? And because there is a clear relationship between this small vector and the outputs of the classifier right here, you can actually learn this function. So locally approximate the predictions of your predictive model or distill it, call it however you want. You can just use a very small proxy network. This can be a two-layer MLP, generate some image variations, and just learn this network to predict what the classifier would predict if the semantic vector was to be changed. Now, what happens after training? Like, why would I even be doing that? Well, the reason is simple, that once I've approximated this response of the classifier, I can now backpropagate through something else than the classifier, right? So I'm not using the gradients of the classifier, I was only querying it and extracting the logits. Now I have a distilled information into a very small network, and I can just play with it. So we propose to do two things with this small network. One thing is you can just take the gradient with respect to the input being the original semantic representation of your image. So you just find the direction of the greatest ascent of your model's predictions, and if your approximation is accurate, then the direction will be influential, right? You can also find some directions connected with the Hessian, and this is a more complex scenario, but here you obtain more directions. So you just increase diversity. And now I want to pay attention that the whole procedure that I described was only for a single image. So doing that for every image would actually be meaningless. But it turns out that you can do that for a single image and use those directions globally across your dataset. So in a way, the diffusion model also encodes the reasoning process of your predictive model, and you just use much less compute, right? Now you can just take your direction, move as much as you want in this direction, and at some point arrive at some place where the generated image modifies the decision of the classifier. So we assess the globality of those directions by simply computing the fraction of images for which the decision was flipped on some batch of samples and observe what happens for G directions and H directions. So an interesting property is that the G direction is actually the strongest one, so we almost always flip the decision, while the H directions actually have this decreasing globality property, as you can see on the plots. So in case of some image examples, on the left you can observe how a single direction influences various images. So here the changes are very small because you actually want to arrive at the decision boundary very close to the semantic difference that is minimal when modifying the image. But you can see the general influence that some wrinkles appear on the faces of those persons. You can also treat the G directions as a source of diversity. So if you use many images as the source image and obtain the G directions, they actually differ in semantically meaningful way. About the H directions, they can also serve as a source of diversity. So if you only have one image, you can just take the G direction, take the H directions, and actually observe that the influence of them is different. And this is also like principled because the H directions come from the definition of the eigenvectors of the Hessian matrix, and those are orthogonal, so you should expect that they differ actually. And the final thing that we also do is we can utilize the fact that we are not just producing a single example that explains the model. We are actually obtaining an entire direction, and you can play with this direction also. So you may want to be interested in what are actually the pixels that influenced my model most, right? I changed some pixels, but how do I know that this is the minimal number? And here we show a simple example where just the absolute difference between the explanation and the original image shows you some features which are actually dispersed around the image, but we propose another method that uses those directions to filter out unimportant pixels and focus on what's actually important. And here we would actually say that your model focuses on the teeth when changing its prediction from old to young. And the formula is pretty simple. We just utilize the standard integrated gradients nested in the semantic latent space of a diffusion autoencoder and also discretize typical gradients, so we do not backpropagate through the classifier. We do that in fully black box manner, but you can find the details in the paper. So now coming to the conclusions, just briefly what I wanted to bring with this presentation. This looks, for me at least, as a very proof of concept work because we do that on data sets that are simple, like face images are pretty simple. We do much more complex things in computer vision. So do black box explanations scale to large data sets like ImageNet? I don't know. It's a great direction to explore, and I encourage you to actually do that, maybe with us, because we are open to collaboration. Another conclusion that I have is that actually there are various interesting modifications of standard generative diffusion frameworks, and finding an application for those extensions shows you that the results are highly non-trivial for XAI. So I also encourage you to read papers purely about interesting extensions. We actually show in another follow-up work that you can use another class of diffusion models or diffusion-like models called Schrödinger bridges, where we limit the explanations to some specific regions. So I also encourage you to visit this paper. Maybe you saw that yesterday at the poster session. And with this, I would like to finish the talk and invite you to the archive link for the GCD paper. Maybe visit the LinkedIn profile or the link of our research group. And I'm also very open to grabbing a cup of coffee or beer and actually talking about XAI, because I really like to talk about XAI, as you might have noticed. So feel free. I can buy you a beer, no problem. And yeah, see you. Thank you.